Welcome back to the LaTeX training. In part 4, we look at architectural rules, defining the desired architecture that we want to achieve, and then implementing rules to make sure that we stay on track. And again, we're going to go back to our ISO AGlib example, where we're seeing lots of different layers. We see that the desired relationships go from hardware drivers, that's used by the hardware abstraction layer, which then is used by driver extension, and then communication at the top. And we've seen that the gray modules here are specifying optional modules, and the green and colored modules are mandatory parts of the system. So how would you go about enforcing this desired architecture? There's a few use cases. Number one, we want to preserve the independence of the gray modules, the linear independence. So for example, we don't want virtual terminal using application layer. We don't want process data using task controller. And so there's a special type of rule in LaTeX called independent subsystems that we can apply to make sure that they do stay independent subsystems. Then if I, as a developer, try to create a relationship that violates that architecture, I'm going to get a message to say that that's not in line with the desired architecture. Then we want the layering to be observed that communication only uses the layer below, and each layer uses the layer below, which is common in a layered architecture. And those are called layering rules. So we have independent subsystem rules, layering rules, and the third type of rule is an API level rule, where we can set on an individual API, for example, that it cannot use another API, or an API cannot be used by a component, for example, somewhere else in the system. And this is perfect for keeping, for example, encapsulation, making sure that there's no data leakage. There's a security use case there as well, making sure that our APIs are locked down. So 3 rules: layering, independent subsystems, and API rules. Let's have a look at those in LaTeX now. Keep this picture in mind for the desired architecture, because we'll come back to this and as we see our implementing of the rules in LaTeX. So let me bring up LaTeX as well. Here we see the dependency structure matrix once more for ISO AGlib. And we've already partitioned this system, and it's revealed that there are some relationships above the diagonal. That is to say, util is using com high up in the architecture, which is perhaps not desired. By the way, util, I would imagine, here is a utility. Utilities should really only be used. They shouldn't consume other parts of the system. So that kind of rule you can also put into LaTeX and say that it should not use anything above it in the hierarchy. So I'm selecting the cells here, right click, and I'm saying that this cannot be used. So this is a cannot use rule that I'm putting here. And now you see in this particular instance, util is using com, and it's using some things in supplementary driver, which we can examine with the information pane. These are violations of that intended architecture, so that's why we see the red flag there. And so we don't want util generally to be using other things. We want it to be a provider. So going back to the independent subsystems, we can see that the part 13, 3, 10, 6, and 12, all according to this picture here, should be independent of each other. So we just select those parts that we wish to be independent, right click, and create independent subsystem rules. Here we see, for example, that we have specified that they shall be independent. However, they are not. They are depending on each other, in that part 10 is using part 6 18 times. And you can see those relationships, what's being used and in which files, by which files. And you see the red flag because this is a violation of that independent subsystem rule that we've just defined. Then the second type of rule was layering. So let's assume that this is our intended architecture, com at the top and the hardware abstraction layer at the bottom. We could then just simply right click here and say create layering rules, and that applies to the whole system. And you can see now basically every relationship above the diagonal is undesirable. We don't want a lower layer calling a higher layer, and that also goes through recursively to our subsystems. And generally we don't want any relationships to be above the diagonal. And now you see lots of red flags or red marks red triangles in the cells that indicate we are violating a rule in the architecture. So it gives us a clear indication of where we need to do our remediation, where we need to get things back on track, and to improve the architecture somewhat. The third type of rule is an API rule. So if we went down into, for example, the utils layer, and we went to util funcs here, let's say we expand, you can expand members for any part of the subsystem. So if I expand members here, you can now see that I go down to the member level, and if I just expand the members, then I can actually set on any of these APIs. I could say, for example, get C string count down here cannot be used by a component outside of its component. I could right click and say, for example, this cannot be used by get C string length. That means this usage is forbidden. Or I could say get C string count shouldn't use any functions above. So I could select what components it shouldn't use. And again, start to lock down on an API level which parts of my system can be used and which can't be used. So this is extremely useful for example, you've got an authentication routine or a control flow through your software, which is authenticating, and you want to keep that, or you've got end-to-end protection going on, you want to stay inside a particular control flow. This kind of rules will help you to enforce that kind of control flow analysis. So those are the three rules: independent subsystems, layering, and API. What about reporting? Well, for any of the rule violations, we can actually produce a report now. If we select other report here, you can see that we have a special report for violations and for rules. And so if I select that violation, you can see I have 97 violations of the architecture as I've specified it. So I can select those rules, I can see those rules in a tabular format, and I can also, I'll go back to here, see those rules that I've set on the system. Okay, so I can check, for example, my cannot use rules, my must use rules, and my should not use rules. And I have 97 violations, and so I can actually save that into a report. I'll save on my desktop. This is now a text file or a HTML file, for example, and I'm just going to save that. And that's my ISO aglib violations in this case. And I could then go and browse that report here and communicate that, socialize it with my colleagues and teammates. Okay, so this would typically also be put into a DevOps pipeline so that there's a continuous compliance, a continuous checking. You can also start to consider that you want to enforce this on a coding level inside developer IDEs and desktops. For that, we have a VS Code plugin, and our VS Code plugin is able to connect the coding environment to the dependency structure matrix. And that's useful, for example, for impact analysis. Just going back to that function that we were looking at for get C string count, we see this function here, and it happens to have a security vulnerability hard-coded into this function, a hard-coded password. And a natural question might be, what's the impact of that vulnerability on our system? Well, you can of course do an impact analysis in LaTeX, as we've seen. In fact, let's do that. Let's go back to LaTeX here, and you can see in that particular function, get C string count, we have the ability to create tags. So we could import that from a static analysis tool. For example, this one here would be a tag for the cert 130 vulnerability, and cert 130 is hard-coded password. You can then do an impact report on the tag inside LaTeX here. So I could do a report and then an impact report on that particular vulnerability. Or I could do it on inside VS Code. And in VS Code, you would see that there's two levels of impact here. At the highest level, get C string count is used by this function, and then the set identification function is used by this function. Well, there's a richer opportunity to explore that on a coding level inside the VS Code plugin by looking at the upstream and downstream reports. You can see, for example, get C string count. There's a used by report that is used by this function here. and then that is used in part 10. And you can actually see the impact rippling across multiple levels of the ISO AGLib system. And similarly, the users report goes the other direction. You can see what a component uses from this perspective. So wonderful way for developers to assess the impact of a security vulnerability or a change by looking at the code, or as I say, you can do that in the dependency structure matrix. So let's go back to our training slide. We've seen how to specify those rules. We've seen that you can produce a report based on those rule violations. And one thing I haven't shown is the must use violations and the must use rule. So for example, here, if a component must use another component, so let's say there has to be a dependency from supplementary driver, it has to use the string class in util, for example, you can actually specify that and say there's a must use rule there. And of course, this is satisfied because util is used by supplementary driver. And so you can actually mandate certain functions are used by certain other functions as well using these rules. So extremely powerful mechanism to control and manage your architecture. That concludes enforcing and maintaining the architecture. Thank you very much, and join us shortly for how to reorganize the system with LaTeX. Thank you.